In this video, we're trying to integrate x times the inverse sine of x. And this requires first a trig substitution, and then we end up in a situation that requires integration by parts. And along the way in that integration by parts, the trig identities get really intense. So this is kind of a two-star problem. So let's start the problem by letting x equal sine theta. And the whole point of that is to undo this inverse trig function. Now this piece, inverse sine of x, is going to be the inverse sine of sine theta, and it will reduce to just theta. So that's our main goal here. Everything else is just side effects from choosing that substitution. I have to transform the differential as well, and that's cosine theta d theta. And then I rewrite my integral after making the substitution. And x should be replaced with sine theta. Maybe I'll illustrate how that works in the inverse sine instead of just saying it. Replace x with sine theta, and I have inverse sine theta, which just gives me theta. And I've got my differential hanging around, so that's cosine theta d theta. Again, inverse sine and sine undo each other, leaving me with just a theta there. And I've got theta, sine theta, cosine theta. So I've got theta right next to a product of two trig functions of theta, and this would be so much simpler if I could write those two trig functions as one single trig function, and thankfully there's an identity for it. The sine of 2 theta is 2 times the sine of theta times the cosine of theta. In other words, this piece is 1/2 the sine of 2 theta. So I'll move the 1/2 out in front. Now this looks like a classic integration by parts. I'm going to let u equal theta because that gets simpler when I differentiate it. dv is going to be the rest of this. And I'll have to guess the antiderivative of that. And then we're going to apply the integration by parts formula. So when we guess the antiderivative of dv, it's basically cosine 2 theta, but there's a couple things to adjust for. There's a minus sign because the derivative of cosine 2 theta gives me a negative sine 2 theta. And we have to adjust for a factor of 2. I need a 1/2 out in front so that when I differentiate this expression, when the chain rule produces a factor of 2, the 1/2 is there to cancel it out. So this is the correct antiderivative that gives me v. Now one really important point here is to not forget the 1/2 in front of the original integral. So I have 1/2 times this integral, and that integral is given by the integration by parts formula now, and that's uv, so negative 1/2 theta cosine 2 theta minus the integral of v du. And since v already has a constant out in front, I'm going to pull that out. That negative constant cancels the minus sign in the integration by parts formula, and the 1/2 sits in front of the integral now. Again, this is v du, and du is just d theta, so I have the integral cosine 2 theta d theta. So now I have to guess the antiderivative of cosine 2 theta, and that's just sine 2 theta, except that I have to compensate for a factor of 2 created by the chain rule. So I have 1/2 times negative 1/2 theta cosine 2 theta plus a 1/2, and then the antiderivative of cosine 2 theta is 1/2 sine 2 theta. When I differentiate this thing, I would get cosine 2 theta times 2, and the 2 would cancel the 1/2, leaving me with cosine 2 theta. Now at this point, I'm not done writing down the solution to this integral, and it's not just that I ignored a plus c. I'll get to that at the very end. The original integral was an x integral, so my answer better be in terms of x. That requires substituting out and replacing theta with the inverse sine of x. And this is where things get messy in this problem, because I have the cosine of twice the inverse sine of x, the sine of twice the inverse sine of x. And we don't know what to do with those. I can do a trig function of an inverse trig function, but not a trig function of twice an inverse trig function. So I have to apply some new identities. And I'll just list those at the top since space is starting to run out here. The cosine of 2 theta is cosine squared theta minus sine squared theta. And the sine of 2 theta is 2 sine theta cosine theta. I'm going to go ahead and distribute the 1/2 into this at the same time, which is a little bit tricky, but we'll keep really close tabs on all these 1/2s. So I have a negative 1/4 theta cosine 2 theta, but I'm replacing that with cosine squared theta minus sine squared theta. Distributing the 1/2 to this second term, that would give me 1/2 times 1/2 times 1/2, or 1/8 sine 2 theta. But I'm going to replace sine 2 theta with twice sine theta cosine theta, and one of those 1/2 is going to be canceled out because of that factor of 2. That leaves me with 1/4 sine theta cosine theta. Now I can plug in that theta is the angle whose sine is x, and that looks like a pretty significant mess, but really there's just one challenging piece to this. I need to find the cosine of the angle whose sine is x. That's this piece, and the square of that same thing is appearing right here. The sine of the angle whose sine is x is just x. So I'll simplify one more time before we get into that issue. And I have the cosine of the angle whose sine is x all squared. Again, we still have to do some work to figure that out. But then I have the square of the sine of the angle whose sine is x. And I get x squared out of that piece. In my second term, that's a 1/4 sine of the angle whose sine is x. That's x. And again, really the only tricky piece we have to compute, the cosine of the angle whose sine is x. And again, I'll try to remind myself to put a plus c at the very end. So the cosine of the angle whose sine is x is really the challenge here. And we solve this by using a triangle. I want to visualize the angle whose sine is x. And we already had a name for this thing, by the way. It's theta. Theta is the angle whose sine is x. So the opposite over hypotenuse is x. And the simplest way to get that done is to let the opposite side be x and the hypotenuse be 1. Then I just have to solve for this missing leg. So I need to be able to square this thing and add it to the square of x and get 1. And you can guess and check your way through these once you have enough experience. I can see the square of this thing is 1 minus x squared. When I add that to x squared, I get 1. If you want to be more rigorous with the algebra, you could just give a name to this. I normally use a question mark. And I would write down question mark squared plus x squared equals 1. Subtract x squared from both sides and take the square root, and you get the same thing. So I'd encourage you to start guessing and checking as soon as you get comfortable with these. Okay, and this means that the cosine of this angle, the cosine of the angle whose sine is x, is the adjacent over the hypotenuse, or just the square root of 1 minus x squared. So finally, I can write negative 1/4 inverse sine x times the square of the cosine of the angle whose sine is x. In other words, just 1 minus x squared. That undoes the square root. Minus x squared plus a 1/4 x times the cosine of the angle whose sine is x squared. Well, that's square root 1 minus x squared. So there's just a little bit left to do. I can combine the two negative x squareds in this term, and I get negative 1/4 inverse sine of x times the quantity 1 minus 2x squared plus 1/4 x square root 1 minus x squared plus c. And we're done. If you find the math content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce dozens of new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.